We're trying to find grams. What was the measurement unit that we were given? Moles. So not the same. We're going to have to do a gram to mole or mole to gram conversion. Yes? Okay. What was the substance that we wanted? Sodium hydrogen carbonate. What was the substance we were given? Carbon dioxide. So we also have to do that. Okay. So we minimally have 2 conversions that we have to go through and do. What I would like you to do is set up some work to try and do those conversions and see what you can come up with. If you've got questions about where to find things or where to get started, just ask. I'll come around and take a look. So we want to address again, we didn't actually write it down, so let's write it down this time. This is what we want. This is what we're given. So what we need to do is look at the unit and decide what things changed. So when we look at a unit is composed of 2 pieces. What are the 2 pieces of a unit? Value is not a unit. That would be making a value.
2 pieces
of a unit. A unit has 2 pieces. Okay, so I heard one part of it, substance. Substance is very, very important. What else is important? I don't quite accept amount. We've been calling it a measurement. So when we go through and look at our question, based off the given information, we can look at the measurement, and the measurement needs to go from grams to, helps if you can see the whole question, it needs to go from moles to grams. Yeah?
Yes.
What is the substance doing?
We have
CO2 going to sodium hydrogen carbonate. So when we're trying to solve this, we minimally have to do 2 conversions. One to address the moles to gram, one to address CO2 to sodium hydrogen carbonate. Okay? Those are the 2 pieces that we need to solve the question. Okay? So the next thing that would come up is, well, which one should we do first? If you don't know, pick one and try. Okay? With a little bit of experience, you'll start to notice patterns behind why you should be picking one over another. Okay? If I just tell you that, you'll be like, I totally know that, until you get to the exam, in which case you won't know anything about what to do. So you need to struggle through some of these options to see what things could possibly come up. Okay? So go ahead with that extra information, see what you can organize, and then we'll start looking at some examples of possible solves. So some people went through, as they were working and struggling, they were like, I know Greg sometimes works on these. And he started to work on it well before any of you started, so he got a little ways into it. Okay? Before anybody actually looked up to see his work, I went back to him and was like, yeah, that's cool and all, but I don't want you to do it that way. Okay? And I went through it and actually started changing some stuff on him, and I said, do it this way. Okay? And in that do it this way, here's what we went through and did. Still the same basic process, right? 2 moles CO2, that's what I started with, end with grams sodium hydrogen carbonate. He's got a number, right? So he got a number, must be right. Okay? Well, did his units all cancel? So it must be right because the units canceled.
Yes.
Okay? Those conversions in those units have to be valid. If they aren't valid, then all he did was throw some random numbers at it and punch it into a calculator to get a number. That doesn't make it valid. Okay? So let's go through and look at those conversions. So the first thing I said, I wanted him to deal with the mole to gram conversion. So we placed moles of CO2 in the denominator, so moles of CO2 would cancel, right? Okay? If we're going to do that to grams, that's going to have to be grams of CO2, yes?
Yep.
Okay? Because that conversion factor is found on the periodic table. It doesn't change between substances, it only changes the measurement. So what he went through and did is he took a look at the periodic table for CO2, and he actually did that work awesomely up there. Fantastic. Okay? So that came from the periodic table. So that is a valid conversion. Right? When he went through and did that, he noticed that he got rid of the moles of CO2, which is good. I didn't want those. And he brought in grams of CO2. Okay? That's fine. Does he want grams of CO2 in the answer? No. Those don't show up in the answer. So what does he try to do? Cancel them out by placing grams of CO2 in the denominator. Okay? Well, at this point, we've already done the measurement conversion, so I need to do the substance conversion. So he's going to convert that from grams of CO2 into sodium hydrogen carbonate. Fantastic. Right? What is the measurement unit that he has to use? Grams, right? Grams. They should be the same because the only thing we're converting is the substance. I can't convert the measurement and the substance. Okay, which means that has to be grams. Also agree. Now he puts in 2 and 1. Where did that 2 and 1 come from? The balanced chemical equation had a 2 in front of sodium hydrogen carbonate, and it had a 1 in front of CO2. Completely agree, it did. What was the measurement unit from a balanced chemical equation? Moles or molecules. So the numbers that have been placed in here have some basis in reality. The units have some basis in reality. But the numbers in the units have no basis in reality. Okay? And so what has happened is we've forced it to happen because we're like, well, 2 conversions, I just got to do it. Okay? Could we still theoretically make this work? So number 1, that conversion is wrong. Okay? I don't have that conversion. So if we try to go through and clean that up, if we're going to use the balanced chemical... Oh, you jerk. See, that one was recorded for the record. Okay? I can't use grams. If I'm going to do a substance conversion, the measurement unit will be moles. Okay, so 2 and 1. I know. Okay? Does that conversion help you? Yes, why?
Because it gives you from CO2 to moles of that. Well, because the substance is from moles to...
It brings me moles of sodium hydrogen carbonate. Yeah, but now
You want to convert that.
I have grams or moles of CO2. I didn't want moles of CO2. That can't cancel with the grams of CO2 over there. Okay? So yes, this gets me closer to the answer. Okay? But unfortunately, it has introduced a bunch of units I didn't want. Okay, so I would need to get rid of those units. How do I get rid of moles of CO2 and grams of CO2? Because I don't want those. Now we're canceling out step 1. What does that mean about the step 1 that we did? It was not a good step 1. Okay? This is where conversions become tricky because you'll go through and start it and be like, well, I know I just want to do this. And the other option would be to undo what I did. Okay? Well, I don't want to undo what I did, so I'm just going to say that this is the way it works. That's not how calculations work. Okay? If you start on a false premise, everything you do afterwards has to follow that premise, even if it means you have to undo that false premise. Okay? This is a challenging concept for students to deal with, okay? For everybody to deal with. Once we decide to write something, guess what happens to the validity of that written statement? It becomes true. Even if it was inherently false, your brain now says that that is true. Okay? And unless you go back and critically evaluate, should I have written that? Every decision you make afterwards is going to be based off of that initial statement. Okay? This plays out when it comes to course scheduling, when you decide on classes to pick. Right? If you think back to how you built your schedule, Okay, you probably sat down with the advisor and said, well, you need an English class, so you picked an English class. Okay? Your schedule is now locked because that English class is there. If you go through and say, well, I need a math class. The only math class that works for me is at the same time as the English class. I guess I won't take math this semester. Why don't you unenroll from the English class, enroll in the math class, and find a different English class? Okay? But because you've already picked your English classes by default, your answer, every decision thereafter is based off of it. You don't go back to critically evaluate, should I have picked that initially? Does that make sense? Right? So every decision we take, we should consider, should I have taken that decision? Go for it, Greg.
This lines up with the principle we saw in the kids' book of pick the colors that are absolutely necessary first, or the ones that are less wiggly. So pick the classes that are harder to find first, right?
There's a million English classes. Advisors should not be telling you to start your schedule with an English class. Yes, you need an English class. There's a million of them. You could get into any one of them. Pick the ones where you don't have a million choices. Those are going to determine your schedule. Those are more important.
How many sections of CHM130 this semester were there?
10.
I think we're at 50 or 60 sections of English 101 in person.
So if you knew you needed chemistry, you should enroll in a chemistry class first, then worry about the English later. Okay?
And we add more. We have the ability to add a lot more than he does because he has to drop in a 50-person course, and I get to drop in a 20-person course.
Yeah. Okay? Which is kind of beside the point, but it's still coming from conversions. Okay? We have to critically evaluate each of our conversions to make sure that we aren't fudging it to do what we want it to do. We're doing what the information allows us to do. Okay? That mole-mole conversion came from the balanced chemical equation. That next one came from the periodic table. A bunch of people said, but we're now undoing what we did. That's fine. Can I still fix it? Yeah. I've now undone what I did. That doesn't mean I have to restart. I just acknowledge that I screwed up early on. I've undone that mistake. Okay? What do I want to do now? Because if we look, grams of CO2 cancel, moles of CO2 cancel. What do I want?
Cancel the moles. You have to get a mole, 1 mole of NaCH and 2 grams.
I want moles of sodium hydrogen carbonate to be gotten rid of. It's showing up currently in the numerator, so I'll draw it in the denominator so that it can cancel out. What do I want in the numerator? Grams of sodium hydrogen carbonate. Where do I find that?
On the periodic table, you got to add a bunch of stuff.
That's in the periodic table. We add it all up. Somebody did it.
84.
84 is close enough for me. Grams of sodium hydrogen carbonate per 1 mole of sodium hydrogen carbonate. In this solve, we again went through and said, well, we had grams to moles and substance to substance. So measurement conversion, substance conversion. We decided to do the measurement conversion first. That was our choice. Does that mean we get the wrong answer? No. This calculation is still going to result in the correct answer. But we had to use truthful facts and conversions along the way. Yes, it means we undid a calculation. Okay? It doesn't matter. We can still get there. You can make mistakes and still get to successful places. That's kind of how life works. Okay? Is there another way we could have done this? Okay? So what I'm hearing, and what your statement is, isn't wrong. Okay? But remember, we started out with 2 things we needed to do. A measurement conversion or a substance conversion. Okay? And so what you just answered is, well, I can just cancel that out. That's canceling it out of work that I've already done. You're really not saying we're changing the method. You're saying use the exact same method that led down a horrible path, but I was able to recover. And now just delete stuff from that. Okay? Was there another path that we could have taken from the outset? In starting this whole question off, CO2, instead of doing the measurement conversion first, I could go through and attack the substance conversion first. Where's the substance conversion found? Substance conversion found. Coefficients from the balanced chemical equation. 2, 1. Okay? So the substance conversion was done. Now what do I do? Is that hard? That looks hard to see. Screen? That was so much better. You're like, I don't even know what you're talking about, Mike. Exactly. That's how much better it was.
Yeah, so you would just,
Sodium. Whoops.
And that's how far I got before Mike stopped.
So there we go. We did our substance conversion first, then we did our measurement conversion. Where do we get the measurement conversion from? Periodic table. 2 paths. Do both of these paths lead to the same answer? Yeah. Okay. They do. Okay, as Aiden was suggesting, the 44.01, I multiplied by it, but then I divided by it. So they canceled each other out. The net result for the top equation was 2 times 2 times 84. What was our result for the bottom one? 2 times 2 times 84. You get the exact same answer. Okay? The trick behind this process is not forcing numbers into units. Okay? That's challenging. Okay? But that's what you have to consider when you go through and make your choices for those conversion processes. Kind of make sense? Okay. Questions? Did we want a number for that? So 4 times 84? 336? 336 grams. Right. Don't ask the question about sig figs. Just don't do it. You don't want to. Okay. That was a substance conversion. Your balanced chemical equation is always a substance conversion. Okay? Try and clean that up. And by cleaning it up, I mean going back to Greg's bad one. Yeah? Nadia, are you still saying no? Am I good? Nice, David. If we go back to Greg's conversion, look at what you're changing. We're changing the measurement. This measurement was found in the periodic table as a valid conversion. When we go through here, we're looking at a substance conversion. The substance conversion comes from a balanced chemical equation. What is the measurement for a balanced chemical equation? And this becomes, the tricky one, is you're using chemical equations with substances you've never seen or potentially heard of and can't actually grab a hold of. Right? This is why we talked about the power of the chemical equation in terms of bicycles, because bicycles were easier to understand and manipulate. This mistake of 2 to 1 is happening because you're telling me 200 grams of bicycle tires and 100 grams of frame equals 1 bicycle. No. That's entirely false. Right? 2 bicycle tires plus 1 frame equals 1 bicycle. The units are pieces, right? Not measurements. Or not masses. Kind of make sense? Okay. So now let's make life difficult. This question should look kind of familiar. This was off of exam 2 or a derivative of it. And it had a plethora of information in it. Okay? Tons of information. Okay? At this point, we've now covered where this information is. The very first sentence, 1 mole of oxygen consumed, 2 moles of water are produced. Okay? So I'm saying if I had 2 oxygen 1 oxygen and water, that I would get 2 and 1. Well, that doesn't look like a balanced equation. The question right before this was hydrogen plus oxygen makes water. Those numbers are coming from a balanced chemical equation. Are you required to interpret a balanced chemical equation?
Yes.
Yeah? So what does that mean about that first sentence? No longer given to you because you're required to find that information. 9 grams of oxygen, 16 grams of oxygen equals 1 mole of oxygen. Okay? Which is a false statement for the record. We had to play around with that. Okay? Where do we find the relationship between grams of oxygen and moles of oxygen? Periodic table. Are you expected to know that? Which means? Okay. 18 grams of water is 1 mole of water. Where is that found? Periodic table. Are you expected to know that? So your question becomes, we'd have to add a little bit more context. If 9 grams of oxygen is reacted with an excess of hydrogen, how many grams of water are produced? You get one piece of information explicitly stated. You're required to know where all of that other information is to do the conversion. Okay? So when we talk about process, I needed you to get a process in place so that when we get a question like this, you can trust the process, and now what you can spend your time thinking about is not how to solve it, but where to find those conversion factors. How many of you are comfortable with the process? That means you're now learning the process and where to find all the conversion factors. The cognitive load on you has now tripled, quadrupled. Okay? That's going to make things more difficult, which means more practice. Okay? This means working questions. This means trying to set up that process and solve through and ask yourself, why am I placing units where I'm placing them? So that when the question changes, you know where to find that information. And you can trust the process to allow you to get there. Okay? That's challenging. Okay? Really, all we've addressed so far is 2 places for conversions. Periodic table gets us a measurement conversion, grams and moles, and a chemical equation gets us substance conversions. Okay? So we've only added 2 more things. Okay? Except there's more content for the class. Okay? That more context for the class is going to bring in the idea of molarity. It's going to bring in the idea of gases, which means more conversions that you have to know where to find. Okay? The core of this is our dimensional analysis, our desired measurement and substance. What do we want? What are we given? And then just a question of establishing a conversion where we have given in the denominator, why? I want to get rid of it, and I want in the numerator. Very often, it is not a single step, right? Which would mean we're going to have multiple different levels of givens and wants, because each of those is now an individual step to shift along. Right? That's the desired process. That condenses it into one system that allows you to manipulate multiple different things at the same time. If you only go through and do individual conversions, you have to memorize a formula to do each of those conversions, which is going to require more cognitive power on you than you're already being taxed with. Okay? So, convert A to B. Okay? So, what are the conversions? What are some conversions that we could see in there for converting A to B? moles to grams. Where did you find that conversion? Periodic table, right? Which means you now have something that you could write down on a note card. I want to do grams to moles. That information's on the periodic table. You now know where to look for that information because you need to know that. Okay? Where else could you find a conversion? Or what other conversions are there? Moles to molecules. Where do we find that conversion? That's Avogadro's number. Okay? That one's a little bit nicer than, say, the grams to moles one because Avogadro's number is a constant. It's 6.022 times 10 to the 23rd. Things is equal to 1 mole of things. It's always that. Okay? The grams to moles will change depending on what? The substance. Oxygen has a different gram to mole than neon. Okay? So you would have to pull different information in to get access to that. What other conversions are there? Grams to kilograms. Where's that one found? What's that? Okay, your head. I thought you said something else. That's fine. Okay, your head. You were asked to memorize that. What other conversions? I haven't done any other conversions, like inches to feet, miles to kilometers. Okay. You don't have it memorized. You're like, boy. Where is it found? The front of the exam. Okay? It's given if you need to use it. Yeah. Or if you could use it. Okay? So you need to know where that information is found so that you can manipulate it appropriately. Okay? If we look at our chemistry one, we could envision a process of going atoms or molecules of one substance and converting that into atoms or molecules of an entirely different substance. Okay? Do we have to go through each of the individual steps that are shown up here? No. It's really going to depend on what the question is asked. Okay? But the core of this is going to be going through moles. Okay? This is why if you went to the stoichiometry session run by the tutoring center, they hand out this worksheet called the mole wheel, where they have moles in the middle and they have everything spider out from it. Why? Because you're converting substances. Right? That conversion of substances is critical to chemistry because that's literally the goal of chemistry. We were trying to convert one thing into another thing. What were those things that we were trying to convert? The birth of chemistry. Lead into gold. That was the whole point. Conversion factors allow us to do that. Okay? We have to know where to find those things. Okay? Other formats that we could look at, measurement conversion factors provided on the exam. Some of the metric ones you need to have memorized. The number of atoms can be found in a chemical formula, okay? Or the number of moles from a chemical formula. Molecules, sometimes we're pushing typically to balanced chemical equations. The number of moles can come from formulas, equations, Avogadro's number. So there's all these different places where we can find those conversion factors. Right? Nearly all of that you're required to memorize. Before you go home and go, okay, I'm going to memorize Na2SO4. That's an example. Okay? What conversion factor does Na2SO4 give you? Individual parts. Give me some conversion factors in Na2SO4. Two atoms of sodium. One molecule of sodium carbonate. That's relating the parts to the whole. That's not what William suggested. He said parts to parts.
So, two molecules of SO4 make up Na2SO4.
Two molecules of SO4 make up sodium sulfate. So the first thing I'm going to say is no on 2 accounts. How many? 3 accounts. Is SO4 a molecule? No, it's a polyatomic ion. So if we fix the language there. How many SO4s are in that? 1, not 2. Okay? And then you related it to the entire piece, okay, which is parts to whole. I want parts to parts. 2 sodium ions to 1 sulfate ion. That comes out of that equation, or that formula. All of those pieces could move in there. Could I also say there's 2 sodiums and 4 oxygens? Yeah. Would I do that?
No.
Why not?
Because you're splitting apart the sulfur.
Okay? Saying the conversion that I need 2 sodium atoms and 4 oxygen atoms is a valid relationship. It's not a relationship I would likely be expected to do because I'm now relating 4 oxygens. As we've talked about this compound, there aren't really 4 oxygens. There's 1 sulfate. Okay? Sulfate is that larger ion. To make sulfate, I need 4 oxygens, yes, but the relationship that we're probably focusing on is sodium to sulfate, not sodium to oxygen. How would we know that? Name the compound. What's the name of that compound? Sodium, sulfur, oxygen? It's sodium sulfate. Okay? The name gives us a hint at the important components behind it. This is why nomenclature can be helpful. Make sense? Okay. So, let's take a minute to get away from numbers. Water and solubility. Okay. We have water shown up here. Greg, what are you doing back there? Those dotted lines, what are those dotted lines called? Bonds, right? What is this solid line called? So that's a bond and that's a bond, right? Wait, why are you saying hold on? Because I like that. Why are you saying hold on?
Going back to what we learned.
Why are they depicted differently?
They are drawn differently. Why would we draw something different if it's the same thing? Okay? Because they're not the same thing. These are 2 different aspects. Okay? They aren't both bonds.
It's like saying putting water in a cup. That's the water.
I have no idea what you're trying to say. You could easily be right, but I don't know what you're trying to say.
Right in your mind.
Okay. Okay? What is the bond between H and O? So if we look at the solid one, we'll call this solid, and we'll call this one dashed. I know it's dotted, but dashed was easier for me. What is the solid one saying?
It's a single bond.
Oh,
Hydrogen and carbon. Or oxygen.
There's a single bond between hydrogen. Well, what is the dashed saying? Okay, so I don't accept that for our solid. What does the solid represent?
Is that how many unbreakable? Not unbreakable, but
There's an interesting statement. Maybe this has to do with the ability to break them. Okay, what do you got?
It says H2O is solubility, and there's a bunch of H2O molecules, and they're all connected.
So the dashed one is breakable, and the solid one is not. So the solid one is not reversible. So I might refer to that solid one as a chemical bond. That other one is breakable. So I could refer to that as a physical bond, okay, or physical connection.
So it's reversible, basically.
Okay? One of those was reversible, one of them is not. So the question is, how do we distinguish those? Okay? One way to distinguish them is draw them differently. We can show them with these dotted lines to represent that as not a formal bond. Okay? Whereas the formal bond would be that solid line, yeah? Right? If we go through and look at this, we see the hydrogen dotted to oxygen. How about the other dotted one? Hydrogen, oxygen. Hydrogen, oxygen. Hydrogen, oxygen. Notice we don't see any hydrogen to hydrogen or oxygen to oxygen. So there's a pattern behind this. Why is the hydrogen only being shown to the oxygen and not oxygen to oxygen and not hydrogen to hydrogen? It's like a magnet. And with a magnet, what do we have? A plus and minus. Okay? Which is really good with a plus and minus. I was expecting north and south. But plus and minus. Where do we get pluses and minuses? Protons and electrons. All of these guys are typically positive. These guys are typically negative. We're looking at a difference between metals and nonmetals. Okay? How did the metals become positive? When they became charged. How did they become charged? When they're paired with something else. What is the charge on that sodium? We heard two answers, which is awesome. I heard a +1 and I heard a 0.
That is a +1.
You said charge, right?
I said charge.
That is a +1.
That is a +1. Does everybody want to go all in +1? You willing to risk your grade?
Yes.
Wait, what?
So Hatem backed out of that. Okay. What is the charge on that sodium? It is 0.
What the heck?
Okay? And we've said this multiple times. What is a characteristic of charge? It is always given to you. Always. Where is it given to you? Top right-hand corner. What is written in the top right-hand corner of this symbol for sodium? Nothing. Its charge is 0. So whoever said 0, good job. Okay. How do I make it positive? Because a lot of you are like, positive, positive. Okay, make it positive. How can I make it positive?
You write a positive column.
Okay, so I could write plus. Now it's positive. Okay. Touche. Fair enough. Hide that positive. I don't want to write positive there, but I still want the sodium to be positive. Pair it with something else. I like that idea. Pair it with something else that's also positive. So let's pair it with another sodium. That would mean 2 positives, which would mean +2, not plus, or it would be 0. Okay, so what should I pair it with to make sure that that sodium comes in as a...
Has a -1 charge.
I can pair it with a nonmetal because when we looked at that line that we literally just talked about, we said the metals all typically carried a positive charge and all of the nonmetals typically carried a negative charge. So instead of pairing that with sodium, let's pair it with chloride. What is the charge now on that sodium? It's a +1. As soon as we move into this compound, it's an ionic compound. The charge on the compound is 0. What do the charges on the sodium and the chloride have to be to achieve that 0 charge? +1 and a -1. How did the sodium become positive? I put it next to chlorine. What did chlorine do to sodium's 1 electron that it had before? It took it away. All right? That's how we generated that charge. Could we use that ability up here? Well, what was the ability of chlorine to take the electron from sodium? Is that something we talked about? The ability for one atom to take bonding electrons from another atom? Yeah, we did talk about that. That was electronegativity. Right? Electronegativity was that ability. And if we look at a difference in electronegativity, if it's large enough, the electrons get entirely ripped away, and we form positives and negatives, formal positives and negatives. Right? Should we be having the oxygen formally rip electrons away from that hydrogen?
Yeah.
No. Why not?
Because then it'd just be useless.
If it did, what kind of bond would we have there?
Wait, say that one more time.
If the oxygen formally ripped electrons away from the hydrogen, what kind of bond would we have? We'd have a cation and an anion, which are both components of what kind of bond? You've literally said the answer when you said cation and anion. It's an ionic bond. How do you know you have an ionic bond?
Metal and non-metal.
Metal and a nonmetal. Is hydrogen or oxygen metals? No, it's not an ionic bond. Okay? That's the easiest differentiator. Okay? So the difference in electronegativity is not enough for the electrons to be completely ripped away because it's not an ionic bond. It's a different classification. Okay? But there is a large difference in electronegativity. And we would know there's a large difference because what? Do you want conversions instead? Okay.
We know their electronegativity.
You've memorized the electronegativity for hydrogen.
We won't know.
Okay, so no. What'd you?
You know the trend for it.
We know the trend.
Right.
Fluorine's the most electronegative. Francium is the least. Oxygen is very close to fluorine, making it very electronegative. Hydrogen being really far away from it means not so electronegative. So there's a large difference there, which means that oxygen is pulling on the electrons in that bond. So it is starting to gain electrons, but it's not getting them all. It just gets some of them. So in the process of getting some of them, it starts to become negative. But it's not the same negative as the chloride. It's a different negative. It's only sort of negative. Okay? How could we depict sort of negative? You don't. You don't depict sort of negative?
We can't have a negative one.
What's the difference between an A and an A minus?
Little f.
See where you're going with that. An A minus is sort of an A, but not all the way, right? Okay.
It's still an A.
Okay. How could we do that with our symbols? Because if I did negative, negative, that would look like the oxygen is... we're not doing multiplication there, guys, but that's okay. It would look like negative 2. Okay? Let's do this. So there's Mike. There's Greg. Right? A little squiggle means sorta. Okay? So we could throw a little... you're welcome. We could throw a little squiggle in there. How many of you want to do little squiggles? No, you don't like that either. Okay.
Tilde. It's called a tilde. Let's have this conversation.
Okay. What did chemists decide to use to represent sort of? Okay. And really, if we think about it, it actually it's rooted in something else. What we're looking at is that the oxygen is starting to change to negative. So we're really saying it's a change. Have we used a symbol to represent change? A triangle, ultimately a delta. That delta over an arrow meant change in temperature. We've added heat to it. It's now become hotter than room temperature. Okay? If we looked at calculus, delta T, or physics, a change in time. Okay? If you don't have to worry about it, don't worry about it. That's fine. So we could use the delta symbol, but we've already used the delta symbol to represent heat, so we don't want to use a capital delta. Never heard it referenced as a baby delta. Let's try and do that not with an eraser. We have a lowercase delta, okay, which is a weird 1/2 as my drawing. Okay, that is a delta symbol in my hand drawing. Okay, I never took Latin or Greek or whatever it was. Never learned that. What happened to the hydrogen in the process of the oxygen taking the electrons? It's starting to be, which would mean delta, transitioning to a negative. If it's transitioning to a negative, where is it getting the electrons from? Hydrogen only comes in with one electron. Where is the hydrogen getting electrons to become partially negative? Oxygen. What charge was the oxygen becoming? Negative. Why? Because it was taking electrons from hydrogen. Why was it taking electrons from hydrogen? Because it's more electronegative than the hydrogen. So the hydrogen is losing an electron, which means it's becoming partially positive. Okay? So let's clean all of that up. Partial positive. Let's try that again. Partial positive, partial negative, partial negative, partial positive, partial negative, partial positive.
So all the red ones are partial negative.
All the red ones, you can do a little better than that. All of the oxygens are partially negative in this case. All the hydrogens are partially positive. Why would we show the dashed line between oxygen and hydrogen? Which formula is correct? I'm going to draw sodium chloride. I want to draw another sodium chloride. Where should I place it? On the other side. Okay.
You can place a 2 next to that.
So here we go. Sodium chloride next to sodium chloride. Is that the proper way that you would imagine to put that together? No. Why not? Which of those is the better way to represent sodium chloride, blue or purple?
None.
Purple.
Purple, why?
Just kidding.
The metal comes first, and second.
Cation being positive. What comes next to it? Anion being negative. What comes next to it? Cation. Anion. Cation. Anion. I would put a negative next to a negative. That doesn't work. Go all the way back to atomic theory. Do we put electrons next to electrons? No. They repel. Why do I see the oxygen next to the hydrogen? There's an attraction. Why is there an attraction? Positive and a negative. Why do I not see oxygen next to oxygen? Why does this one not make sense?
It's like a magnet. You can't put two positives together. They go zoom.
It's like a magnet. You're putting two charges next to each other that don't like each other. They would repel. Okay? This is basics behind how we build this. This is how we built atoms, was off of the same repulsion. When we talk about things dissolving, we're typically talking about salts. Why would salts dissolve well in water? Describe salt to me. It is an ionic compound. Because it is an ionic compound, I have sodium positive and chlorine negative. What could that negative interact with in water? It would interact with the hydrogen because the hydrogens were positive. I can interact with a lot of those water molecules, which means the chloride will now favor interacting with the water than with the sodium. And the ionic bond breaks. It is that balancing out of charge that's causing our water to dissolve things. If water was not polar, as in it did not have those partial charges, guess what happens? It doesn't dissolve. Okay? Have you ever tried to add oil and get salt to dissolve in it? You're like, no, I would never try that because it's not going to happen. Why does it not happen? When we look at the configuration for oil, all oil is a bunch of carbons and hydrogens. The difference in electronegativity between our carbons and hydrogens is not significant enough to generate a charge that would interact with sodium and chlorine. That's why it doesn't dissolve. Okay? So when we think about solubility, its ability to dissolve it is dependent on that ionic interactions. Okay? The balancing out of those charges. Where did those charges come from? Where on the periodic table does it say the charge for any atom?
You're supposed to memorize the column
You could memorize a charge that is common for an individual element. That is not on the periodic table. That is something that you could write on the periodic table. That is not on the table. Where's the charge written on the periodic table? It is not. How do you decide if a molecule is charged?
if it's given on.
Okay. How do we tell water has partial charges? Water says nothing about partial charges. You are responsible for knowing that water has partial charges.
Because of the compound, you know that if it's next to something, it had to have a charge to bond together. Like H2O.
When we look at H2O, what is the charge on the oxygen? It's 0. What is the charge on the hydrogen? 0. When we look at sodium chloride, what is the charge on the chloride? -1. What is the charge on the sodium? +1. Why the hell did it all of a sudden switch on me? What is the difference between the bond between sodium and chlorine versus the bond between oxygen and hydrogen? Ionic versus covalent. How do we decide if there's partial charges? Oxygen has a partial negative charge. Hydrogen has a partial positive charge. How did the oxygen become partially negative? Okay, so we'll put it this way. Go back and watch the video. Solubility curves. We've got a curve here representing the different solubilities of sugar in water according to temperature. What happens when you dissolve a compound is you break it away from other molecules. That's it. What happens when you increase heat? What is that energy doing? It changes phase. What are you doing to those individual molecules? You're separating them away from each other. When you add heat versus you dissolve a compound, what are you doing? The exact same thing. Which means if I increase heat, what should happen to the solubility? It should also increase because both of them are doing the same thing, breaking those molecules away from each other. All right? Let's take a look at this curve for sugar. What does it mean if at 60 degrees I've dissolved 200 grams of sugar? What can you tell me about that point? There's interesting. You're pulling it saturated as a term. Where'd you get that from? Oh, the top. Awesome. Taking advantage of the slide to give you some context. There's some information up there that tells us why we would have those different things, right? Okay. So what do you think? What does saturated mean? You are saturated with food. What happens if I give you a Thin Mint? That was a Life of Brian reference, I think.
Super saturated.
Okay? If you're saturated, you can't take any more in. If I look at 60 degrees Celsius, I've got 200 grams. What does this line represent?
Saturation.
That's the saturation limit, which means this blue point is unsaturated. I could dissolve another 75 grams of sugar. Right? What if I was at 350? At 90 degrees Celsius. Interesting. Okay, so we get some people laughing at that. Our graph has two axes. You have to interpret both when you go through and evaluate a data point. Okay, so at 350 grams of sugar, okay, 90 degrees Celsius, I'm still unsaturated. What if I cooled that now, that same 80 degree sample with 300 grams of sugar, 350 grams of sugar, to 20 degrees Celsius? Okay. I've cooled to 20 degrees. I still have 350 grams of sugar there. If it's all dissolved, I'm above the saturation curve, which would mean super saturated. Okay? Should it dissolve? There is more solid in there than the liquid can handle. Should it dissolve? No. And in fact, if at 20 degrees Celsius we tried to dissolve sugar in it, in water, we're going to get to 200 and that's going to be it. We'll never be able to get up to 350. Okay? So what does that mean? We're at a super saturated sample. Could we take advantage of that? We could put a little string in that jar and we leave it alone for a little bit. What happens? The crystals form around the string. Until what point? Till it gets to the saturation curve. But I would get 150 grams of sugar crystallized on that string that I could now swing around like a sugar mace. Okay? Why not? Okay? That's our difference there. You've already done this, or rather you watched some idiot already do this. This was that sodium acetate trihydrate where the guy stuck his hand in the jar and it crystallized around. That's what's happening. When you generate a supersaturated solution, you've somehow tricked the solid to stay dissolved. All you have to do is kind of give it a wake-up call. What could that wake-up call be? Could be a subtle change in the temperature. It could be your hand. It could be adding a string to it. It could be yelling at the jar. Because what does the yell do? Vibrate. That vibration causes a ripple on the surface that can break the surface tension enough that it'll start to crystallize. Once it crystallizes, it's going to continue to crystallize. Okay? So, neat. There's a solubility curve. Do all substances increase? If we take a look at salt, salt, interestingly, does not increase its solubility. Okay? Why? Properties of the salt. Okay? Every compound has different intermolecular attractions, which we'll talk about in Unit 4, and those attractions mean different things. Okay? If we look at a much more complex curve, you will notice that under most circumstances, what happens with each of these lines? They all increase as you add temperature, because what are you doing? You're breaking apart those molecules away from each other, which is the exact same thing you're doing when you dissolve a compound. You're breaking them apart. So when we add heat and try and dissolve, they should increase. Do all compounds do that? Some compounds don't. Okay? Those compounds tend to get studied for other reasons. Why are they not doing that? Why are they going against the trend? Okay? Why are there people that are able to not do the homework score well on a test? Okay? Why are there people that are able to do all of the homework but then score poorly on the test? Those are people we want to figure out what's going on with so that we can help and fix that. Those are outliers to the system. Okay? Kind of make sense? So, how do we measure them? So here's a reaction. What type of reaction is this? Which, for the record, is on the next exam. It is a double replacement. I want to quantify the amount of silver bromide. Okay? How would I quantify it? What measurement would I take for the silver bromide? Why would you do grams? Okay, moles to grams is a conversion, not a measurement. I want to just do a measurement of the silver bromide. Moles. So I can go into the lab and I can measure moles. No. So measurement. I want a measurement for the silver bromide. Liters. Okay? What phase is the silver bromide? It's a solid. So if I take the silver bromide and I try and measure its volume, that's going to be difficult. I could put it in water to measure the volume, yep, and that's going to complicate things. Is there another way I could measure it? I can weigh it, just determine the mass. Okay? What if I want to determine where it came from? What made silver bromide? Aluminum bromide and silver nitrate. Pick one.
Silver.
Silver nitrate. How do I measure the silver nitrate? Why do you say liters or volume? It's aqueous. So when I take that measurement, I'm taking it in liters, probably milliliters. Okay? Is that milliliters all silver nitrate? What do you mean? It's dissolved in water. Okay, so when I measure that volume, it's not all silver nitrate, it's a bunch of water. Was water necessary to make silver bromide? No. Which means if I look at that strictly, the amount of volume I'm measuring doesn't directly translate into the mass I'm measuring. I would need a conversion factor to know how much silver nitrate was dissolved in that water. Okay? So I would need that relationship. That relationship for chemistry is known as molarity. It's the moles of the substance divided by the liters of the solution. What does that look like to you? It's a conversion factor. Here's your next conversion factor that you get to go through and use. Yay, conversion factors. Okay? That's where we'll go ahead and stop today.